Now, shall I make today's project out of a piece of brass? Shall I make today's project out of a piece of steel? No, actually, I'll make today's project out of a piece of my next door neighbour's front railings. Mr. Crispin here once again, and welcome to my workshop. Now, the topic of what material should I use or why did you use that material comes up in just about all of my video comments, and I wanted to put something together just to explain the basics of what materials are typically used and why you might use them. Now, I learned most of what I know on this topic from an early engineering mentor of mine, Richard Gibbon, and today I'm going to take you to Richard's workshop and I'm going to have a chat and try and extrapolate some information from him as to why you might use what material. Well, here I am in Richard's workshop, and thank you, Richard, for having me. So here in Richard's workshop, I've got him here with me, and we're going to talk a bit about materials. So thank you, Richard, for joining us.
It's a pleasure.
And thank you for joining in and doing a bit of YouTube. I'm sure the audience will be pleased to meet you. And to kick off, I'm just going to mention a few caveats of our discussion. And the first is that we're going to be talking here about general materials, so steels, brass, bronze, cast iron, etc. We're not talking about the specifics of EN24 this or more specific material categories. And also we're going to be talking generally about the materials associated with steam model engineering. There will be a bit of overlap with internal combustion, but Richard here is the steam expert, and so I want to get him on topics relating to the building of steam locomotives and steam engines generally. So unless you've got any starting comments, Richard, we'll kick off.
No, I'm ready to go.
Okay, so I've divided this into three sections. We're going to discuss general material types first and some positives and negatives of the common materials that you come across. Then we're going to talk about a topic called friction pairs, which is how the metals interact with each other. And then to finish off, we've just got some general points of interest to mention. So let's kick off with plain old mild steel. Mild steel being the chassis, the wheels, the all sorts. What's your...
One of the things that we immediately think about with mild steel is that people see a lovely slab of mild steel with bright edges and think, oh, that's lovely, that's perfect. But it's not. For us, we want to distinguish between bright mild steel and black mild steel. Black mild steel is actually the material we really want underneath it if we're making a component out of steel. And the problem with bright mild steel is that although it looks lovely, because it's been cold rolled, it has stresses included in the surface.
Exhibit A. Now this is a piece of black mild steel, this is a piece of bright mild steel, and what's actually in there is very similar. However, there's one significant difference that is what Richard and I have just been discussing. Now, they both go through the same hot rolling process, and at the point of hot rolling, this is finished. The black mild steel, hot rolled, is straight out of the rolling mill, and it looks like this. The bright mild steel is taken and it's put back through the rolling mill when it's cold, and that gives what is really a much more pleasing piece of material. Its geometry is a lot better, it's square, it's straight, and its dimensions are much closer to nominal size in the cross section. But as Richard said, the question of stress relief must be considered. This process of putting it back through the rolling mill cold induces all around a layer of stressed material, and machining can release those stresses. Now, if I was to take this to the milling machine and hold it somehow and run a face mill along here and take half a mill off, when I release the clamping forces, this side has been stress relieved, this side hasn't, and it will bow. So you'd end up with a bow in this shape, and not being a betting man, but I would suspect that in the middle you would detect a bow of between 0.1 and 0.2 of a mil. Less of an issue with turning.
Yes.
Because generally as you take the first roughing cut, all those stresses go. But
on the frames of a locomotive, You really want black.
Case in point with the locomotive frames is that imagine you've put this datum surface on, and then you come to do this side with all these big cutouts. The tendency is for the material to do that. You've released more stresses on one side than the other, and depending on what order you've done it in, you can get yourself in some trouble. Now here I've used black mild steel, and so the stresses are far less, and that's less likely to happen. You can of course go about it a different way. If you really want to use bright mild steel, you could leave material on all round, rough it all out, then go back and finish it all, but really black mild steel does the job fine. With that said, back to Richard's workshop. Okay, so that's the main, if you're going to go down the mild steel route, that's the first thing to think about, black or bright. But why would you use mild steel? I guess it's cost effective.
It's cheap. It's strong, and it can case harden. It's okay. It's fine, and it's a good model engineering general purpose material.
Yeah. So mild steel, I'm sure everyone's familiar with it. It is ferrous, so it goes rusty, but providing you pick the right, black or bright, and you consider the stress relief, if you are using bright mild steel, it's the bread and butter of most constructions.
Yes.
Locomotives underneath, pretty much all mild steel.
And of course you can harden it with case hardening,
Yeah.
so that's a bonus for later.
Yeah, Tubal Cain had a video on that, I believe, showing how you can actually heat treat mild steel and harden it via the case hardening process. That is one downside of normal mild steel. The carbon content isn't high enough for it to actually harden via heat treatment alone.
Yep.
So on the topic of steels then, mild steel is the bread and butter.
Yes.
But other variants, so we've obviously got silver steel and gauge plate.
Let's talk about silver steel. Silver steel's a really useful material for model engineers. It isn't expensive, but it's not too easy to turn. It's hard to get a good finish. But one of the things you can do if you're innovative with silver steel for things like crank pins is that if you don't present a turned surface, so example, if you want, silver steel has a beautiful finish on the OD, so if I wanted to make crank pins, I would use silver steel to get the nice finish on the outside. I would turn down the bit that has to fit into the wheel, and then I would put a colour over the outside. So what you do is use the quality of the material, which is the superb finish,
which is the ground finish,
for the bearing material.
Yes, and the Americans, by the way, refer to that as drill rod. So
yes,
silver steel
drill rod.
So we've seen mild steel in its two common forms. Now let me introduce silver steel, or drill rad. And what's actually different between here? Well, what we're looking at is carbon content. Mild steels have a carbon content of typically less than 0.3%. So of the overall material, less than 0.3 is carbon. Medium carbon steels have typically between 0.3 and 0.6% carbon, and high carbon steels have 0.6 upwards. Silver steel, typically you're talking 0.9 to 1% of the material being carbon. Now, not only does that make it tougher, but it allows for heat treatment. Once you get above 0.3, 0.4, you can start to heat treat by heating alone. Below that, in the case of mild steel, you harden by adding carbon through case hardening. But once you get above that number, 0.3, 0.4, you can actually just harden it through heat treatment alone. Now, silver steel does have a brother, and that is what's often called gauge plate or ground flat stock. Very similar material, just in flat form, and this comes in all kinds of sizes. Again, it's ground, it's a very precise material, and the carbon contents are up there, 0.9, 1%, allowing you to heat treat it. Now, Richard mentioned about being able to use the material's natural advantages to, aid the manufacture process, and he was talking specifically there about using silver steel for crank pins. Now, silver steel comes from a process called centerless grinding, goes straight through a setup of wheels, and it gives you a material that is very accurate in terms of diameter, very round, very straight, very nicely formed. And case in point, it was crank pins that Richard was talking about. Now this illustrates a difference of approach quite nicely. I would probably get a great big chunk of silver steel and then machine it all over. What Richard was suggesting was he would just take the silver steel with its nice ground finish and use it directly, and then just use a collar to make up the spacing that's required to keep the common rods off the wheel faces. So yeah, a nice illustration of differences of approach, and as Richard said, you can often use the material's natural advantages. Well, that just leaves in the steels category a bit about spring steel.
Yes, model engineers have always, and I've always hated it from the very start, using Tufnol leaves to make springs, and it's a sort of plastic and it looks plasticky. So I've developed a technique for using spring steel whereby the top leaf is realistic, but the leaves below, I make a punch, and the leaves below are punched out like Meccano to weaken them, so that you can make a spring out of effectively, well, you can make a realistically performing spring, and we'll come to that when we see.
I'll show you a quick
Locomotives
example
later.
of that.
So these springs, if you look, they've got really thick leaves, prototypical leaves, but in fact they're weakened inside. So it is possible to make proper springs.
And the issue here is that if you use pure spring steel for the size of a model locomotive, the spring force is too much and it doesn't give you any
scale.
It won't spring at all.
Yes.
So what Richard does is he drills holes in that to make the spring steel weak enough but still be of all the right proportions.
And it looks smashing until somebody takes it to pieces.
Yeah.
But it doesn't matter. It looks like a proper spring with a buckle.
And it works like a proper spring.
Yes, it does.
Finally on steels then, stainless steel. Is that much used in locomotive building in your experience?
Well, cladding, stainless steel is good for cladding. I don't really use stainless steel very much. I suppose you'd use stainless steel perhaps for an ash pan on a steam locomotive.
Well, come to think of it, there is one case in which I use stainless steel, and I expect Richard did as well, and that is for the manufacture of piston rods and valve rods. These components are obviously continually inside and outside of the cylinder. They get exposed to steam, they get exposed to air, and a non-rusting material such as stainless is, advantageous. You could use silver steel, but I think rust would become a problem. So there is an example of stainless steel on this locomotive. Okay, then moving on to the next sort of common materials, we've got, your brass and coppers.
Yes, this really is, I suppose, what I'm here for. We think that brass is fine for, it's corrosion free, and you can use it to make bushes, but really it's horrible stuff. It's fine if it's not in a hostile environment, but I've built a lot of boilers, and what you mustn't do is to use brass in a boiler. I wouldn't use brass for bushes, for motion bushes or anything like that.
So that's two topics there, but to take the motion bushes one.
Yes.
So, I mean, a phosphor bronze bush is the common. Brass is obviously a similar material in some respects, it's self-lubricating, but why wouldn't you use brass for a bush?
Right, because there is a horrid thing that happens to steam boilers called desyncification, which over a long time the zinc can emigrate from. Brass is a mixture. It's not a. We've got to distinguish between.
So brass is made of zinc and copper.
Yes, and it's a mixture which is made in the melting pot, but the zinc can come out. And if the zinc comes out in a steam boiler, what happens is that you start to get porosity, and then the fitting actually breaks off. In my early days when I was making little locomotives, I couldn't understand why water gauge fittings you know, broke off when I tightened them.
Yeah.
And desyncification is the enemy of steam boilers.
So watch out using brass on your steam boilers. The zinc over time suffers from a process called desyncification. It exits the brass and leaves the brass slightly more porous.
So make your bushes out of copper or phosphor bronze or gunmetal.
And when we're talking about bushes here, we're not talking about, you know, a bush that the shaft runs in.
No.
We're talking about boiler bushes with a tapped hole where you screw the steam fittings in. But on the okay.
And the bush is there to thicken up the copper plate, because
Yeah.
you know that a steam water gauge is going to be screwed into the back of the boiler, but you don't want to be screwing it into the copper plate. You want to screw it into a nice thick bush that's got plenty of room for the thread.
Yeah.
But please, not brass.
Not brass. Okay, no brass on the boilers. So we're talking about brass in other scenarios there. Do you use brass elsewhere on the locomotive?
Yes, you can use brass on the water pump.
Yeah.
So you can use brass in various places, so cylinder covers, things like that. But you know, balance pipes. I tend to accumulate material, and I'm hoping that every model engineer watching this video is always on the lookout for material. But beware gifts.
Yeah.
Because they can be dreadful. Okay, so, oh, hang on, brass for bodywork.
For bodywork, yeah.
Perfect.
So all the panelling, you've got copper there, but
Yes,
that could
I've
be done in
got
brass.
copper tanks, but that could be. I happen to be given some sheets of copper,
Oh, so yeah.
so it's a gift and it's free.
They were for Angela's art project, but they're now on the locomotive.
They are now on the locomotive. Yeah, this is my 17th locomotive.
Yes.
My goodness me.
My goodness.
Yes.
Yeah. Oh, and whistles. You got to.
Well,
and
yes.
steam domes.
And the covering of the dome, you know, fittings. I would use brass for decorative stuff, I suppose.
Yeah. Okay. Right. And that just leaves us then with the slightly nicer variants of that type of material: phosphor bronze, gunmetal, and copper.
Nicer.
Nicer in terms of performing.
Nicer in terms of performing. Horrid tapping and drilling. I mean, anyone who's had a lot of experience of working with materials will know that you've got to have really sharp tools to turn phosphor bronze, and you've got to have really sharp new drills, because what happens is that as the drill goes in, well, I suppose if it's a worn drill, you're in big trouble because it tightens in the hole.
Right.
So I think sharp tools are the answer for phosphor bronze.
Yeah. Well, it's a wonderful material.
It
I
is.
mean, we spoke about boiler bushes, but also the running
Bearings.
bushes, bearing bushes.
Bearings.
So I'm not sure if you can see Richard's locomotive there.
No,
It's just out of
possibly
shot, but we'll show you some examples in a minute. But so yeah, where axles are running, sliding components.
Yes.
And so why is bronze good for that?
Why is bronze good? Because it doesn't gall, it doesn't tear, and bronze has the ability to sustain itself under difficult conditions. So if the lubrication is suspect, bronze will hang on longer than other materials.
And I guess in the category of self-lubricating materials, bronze is in there.
Yep. So it's not really self-lubricating like white metal is it? I mean, bronze is the perfect material for the bushings and sliding parts. When you buy castings for a locomotive, you would buy, I mean, I don't use castings, but when you buy castings, they often come as gunmetal castings, and they're a delight to machine. They can have porosity in them, but gunmetal is not like phosphor bronze. It resists corrosion like phosphor bronze. It's okay, but again, you've got to beware of porosity in the casting. So we need to look, when you get a piece of gunmetal bar, nowadays gunmetal bar comes as continuously cast material, and it's wonderful. But somebody will give you from their scrap box a chunk of gunmetal which is full of holes. So
Yeah. Beware of
we're
the
back
gift.
to beware of gifts.
A quick visualization of these materials. Here you can see some bronze. That is just you know, the plain bronze bar stock that you get and machined down. Someone will probably criticise my use of mild steel on mild steel for the axle box arrangement. Doing it today, I may well come up with a different combination, but that's how it is. Now, what else have I got here to show you? Here is a piece of brass. Most people will be familiar with that. And here is a piece of phosphor bronze, just plain bar stock. Now, the main difference between them in terms of visual appearance is the colour. That's about all you've got to go by. Once you get used to looking at bronze, the brass suddenly looks very yellow. So that's how I normally distinguish the two, just by colour. Richard mentioned water pumps in brass. Here's one I made for this locomotive a long time ago. All solid brass, silver soldered together, so water will not be a problem. Equally, gunmetal. This is a little engine I made when I was 14. It's a Blackgates twin, double acting oscillator, and the castings on this are all gunmetal. So again, you can see it's a very similar colour to the bronze. And well, I say similar colour to the bronze. This is actually a type of bronze. The main difference between phosphor bronze and gunmetal is that gunmetal has zinc in it, a very small amount, about 2% I believe. So phosphor bronze is pure, oh, we're testing me now, copper and tin, and gunmetal has the addition of zinc. That hopefully gives a bit of a summary of steels, brasses, bronzes,
Yes.
the kind of materials that's used on locomotive building. And what I now want to do is pick Richard's brains on a topic called friction pairs. Now, in my experience in the engineering workplace, the most common friction pair is between the machinist and whoever happens to try and talk to him or her. But Richard, tell us what a friction pair is and why it matters.
Well, the topic has a very posh title called Tribology, but it's about the way one material works within another. And that there are friction pairs which we as model engineers must use.
Avoid.
Avoid. Mild steel against mild steel is dreadful.
Stainless steel on stainless steel.
Dreadful.
Dreadful. So when he says dreadful, what we're talking about is two metals working against each other that gall
and tear
and don't ride on each other. So so friction pairs then. A common question I got through all my cylinder block machining was, hang on, you've used cast iron for the bore,
Yes.
and you've used cast iron for the piston.
Yes.
Surely similar metals on similar metals is bad.
No, it's not true of cast iron. Cast iron is the exception to the rule. I mean, cast iron is, for me, a wonderful material, except that when you've finished a day's machining with cast iron and you blow your nose, you know that something terrible's happening, because it's awful stuff. But once it's in a cylinder of a locomotive, there is nothing to touch it. It contains free graphite. Cast iron contains 5%, I believe, free graphite. And that free graphite is in the form of lubricating surface. And so you can run cast iron. If we look at these locomotives around this room, they've all got, all except this one, they've all got cast iron cylinders, cast iron pistons, and cast iron piston rings.
So you got,
and,
yeah.
And the Wren, which is 40 years old this year, still hasn't got bedded piston rings.
Mm-hmm.
They haven't fully bedded, which is ridiculous after 40 years use. The ring has not fully completed the bedding pattern, and I find that remarkable. I've always been neurotic about lubrication. I fill the cylinders up with oil, and people think I'm mad. But you know, the oil soaks into the cast iron, makes a great big pool in the back of the car, and is very unpopular. But you know, it's a wonderful material.
Yeah, so cast iron on cast iron
is perfect.
It's the exception to the rule of no similar metals.
Yes.
And you know, no similar metals meaning you don't want both parts of a moving assembly to be made of the same metal. But cast iron's the exception there, and Richard's laid out why. Free graphite, self-lubricating, and it retains oil.
So if anybody's giving you lumps of cast iron, accept them.
Yeah.
Gleefully.
What do you need to know about cast iron when it comes to cylinders? Well, you told me.
Go on. Remind me.
Fine grain.
Oh yes, sorry. So when we come to the pistons and the piston rings, we need to use a finer grain, a finer grade of cast iron. So you can't use sash weights from an old sash window to make piston rings from, because that's come out of a foundry and was all the sort of oddments thrown in. When you come to make the piston rings, we need to use something called meionite, which is grade 17 cast iron, and you can buy it in small quantities from model engineering suppliers.
Yeah.
And you can buy a sort of 2-inch bar, 2-inch long, from which you can make 18 piston rings.
Yeah.
So
yeah, that's just one point on cast iron. Beware of the grade of. That is one place where you have to beware of the grade.
Yes.
In terms of its running, you want fine grain cast iron or meionite, where
Yes.
you know, where things like cylinders are concerned.
Because if you cast iron is brittle, cast iron has very bad mechanical properties, and Crispin in one of his videos has been making piston rings and showing how you have to heat treat the piston ring to get it the
I
right
showed how
shape.
not to do all this.
No, you got it right in the end.
Right in the end.
You got it right in the end. Yep.
So let's say I'm going to be making pieces, and a lot of locomotive pieces like my slide bars are in steel.
Gauge plate is good, or you could use, I mean, you can't use bronze for a slide bar, it's got to be steel looking.
Yeah.
So I would use, I suppose you could use mild steel.
So you'd use steel for the slide bar, but
Yes.
what about the friction pair?
That's where you can choose to use either, I mean, generally, one of the things I've done is to use brass for the shoe, but to line it with white metal.
Ah, right, okay.
So
white metal's one we've not mentioned yet, but
oh, sorry.
So just explain what white metal is, and to the Americans this might be referred to as babbitt sometimes.
So this is a sort of alloy of very little lead, tin, and it's like a solder almost.
Normally used as a lining.
And it's a lining.
Yeah.
So car engines have always used white metal because it's perfect against a cast steel crankshaft. So
white metal's applied a bit like a lining that's then machined or scraped afterwards.
Yes.
And for the purposes of visualisation, here is a photo I took at a steam mill which I visited. They were doing a bit of restoration, and what you can see here is half a shell of some kind of bearing cap, and it is lined with white metal. You can see about a 1/16 of an inch thick. This lining is providing the running surface within this brass or bronze casting.
And the white metal is very soft, and if we go to mainline locomotives where white metal was used on the bearings, it's very interesting this, because if you think of something like Mallard doing its high-speed run, that had white metal lined bronze. So the bearings, the crankshaft was made of forged steel, the bearings were made of bronze, and then the inner 1/16 of an inch was white metal. And so sensitive is that white metal on a locomotive like Mallard, where there is not the cooling that there should be, that if that bearing overheats, the white metal melts.
Oh, right.
And you're in trouble. The bronze will get you home. When Mallard did its high-speed run, the temperature rose so much that the white metal melted, and they had a stink bomb on the bearing, which went off and it let off a smell of hydrogen sulfide, so that everything smelled dreadful for the crew, and that stopped the bearing getting really badly damaged.
Oh, right.
Because the bearing was overheating. So the driver's supposed to slow down, but Joe Duddington didn't slow down. He knew that the stink bomb had gone off, and he pulled the throttle open wider,
right,
because he knew he'd only got a few seconds to get the record. It's a
right.
lovely story.
Oh, right, very nice.
So
but yeah, so white metal, batch friction pairs. So you've got steel
Yep.
or gauge plate, slide bar.
Yes.
You can use white metal as the friction
yes,
pair, or
yes,
bronze.
or bronze, or gunmetal.
Or gunmetal. So there's
But not brass.
They're not brass. Okay.
Yep.
Hardened steel then.
Hardened steel.
If I've made a slide bar and hardened it, what do the friction pairs remain the same?
Yes, you can use hardened steel against hardened steel, but my goodness me, the lubrication's got to be dead right.
Yeah.
I know.
So a more forgiving friction pair
Yes.
would be huge bronze.
Yes.
Yeah.
Or white metal.
But yeah, in a lot of the older locomotive drawings and documents, they do tend to specify case hardened or case hardened or hardened gauge plate, and in that scenario you need the right lubrication.
You do. Well, you need the right lubrication, whatever. I mean, in any engineering thing, you need the lubrication.
So to finish up then, we've discussed the different kinds of metals that we typically use. We've discussed them as friction pairs. Are there any other key points you want to mention?
Well, the ability of materials to join.
Yeah.
One of the things that really matters is that for bodywork, you need something that you can solder, or, I mean, I'm not talking about a boiler now, I'm talking about making the bodywork of a locomotive. You need to be able to use brass, and you need to be able to soft solder, and that's a skill which every model engineer must have.
Yeah, silver soldering, soft soldering, do the metals work.
And some brasses, as aluminium bronze, can't be. I mean, aluminium bronze is a very sophisticated material, but I don't think it can be soft soldered.
You normally find someone somewhere has a particular alloy of solder that can do, you know, but by and large, it's not common.
So if you were putting together little pieces, so imagine a cab, and you wanted to put the spectacle plate in, then you'd turn the spectacle plate and drop it into the hole, and then you'd soft solder it using a soldering iron or a butane blow lamp.
Yeah.
And get a nice ring of solder. So the ability of the material to join is paramount.
Yeah. And just about all model locomotives you see that are built up to probably the size I'm going to show you at the end of this video, I'd say that by and large they have copper boilers.
All have copper boilers.
Why is copper the chosen material?
Right, okay. So you need a copper boiler. I mean, people will disagree with me on this. I mean, I've built many locomotives and they've all got copper boilers. You can build boilers out of different grades of copper, and you can now weld copper boilers, but I use copper because it silver solders so beautifully. And I know there's been a lot of fuss about easy flow and whether it's got cadmium in it and whether it's not. I find the modern silver solder that you get from the suppliers, which is cadmium free, is perfectly good for soldering. So with the right flux and with the right solder, you can build a boiler which is safe. And
so the copper is a good balance of allowing you to form the shapes.
Yes.
So with copper, very easily annealable, all the shapes can be formed. And I mean, steel boilers do occasionally crop up with the bigger.
Yes.
Obviously, full-size steam boilers are all steel.
And I'm about to go on a course which is being run by the Southern Federation of Model Engineers to learn about how to care for steel boilers, because at the moment my experience is limited to copper boilers.
Yeah. One final one to wrap up on then that sort of covers all these topics. What about if I said to you cast iron locomotive wheels?
Right, okay. So cast iron is really the craziest thing to make a locomotive wheel out of.
I'll explain that. When you go to a model engineering supplier and you say, okay, I'm building a springbok, I want a set of driving wheels, they come in cast iron. You know, for any locomotive you are building, the wheels are typically supplied in cast iron. But why is that a problem?
Because it's got 5% free graphite in it, and is slippery as hell.
Yeah.
So why would you want to build a locomotive with slippery driving wheels? You wouldn't. What you want is a locomotive that maybe has cast iron centres to the wheels,
Yeah.
but has a tyre on the outside,
Steel
which is
tyre.
a lot of faffing.
Yeah.
And many of my locomotives have the wheels machined out of great big discs of mild steel.
Yeah.
So you avoid the tyre issue. So we're just
So cast iron wheels, cast iron being self-lubricating gives you a slippery wheel, and cast iron on mild steel, not a great driving pair. Okay, so that has pretty much covered most of the topics.
Good.
I hope we've not overdone it.
No.
Or, well, I hope we've not overdone it from the viewer's point of view either.
We'll find out.
We'll find out. So, any closing remarks, Richard?
Well, no, I'd like to sort of share the idea that making things is really the most wonderful way to spend time. I've been an engineer since I was a very small boy, and I still get a heck of a whiz out of making things and imagining how I'm going to make it, and then coming up with the goods.
So hopefully that was useful to somebody. It was nice to sit with Richard and go through it all again, and I did film a workshop tour while I was there, and I will release that as my next video. Apart from that, I hope you found this interesting. Thank you for watching, and see you on the next video.